So I added a PageRank question 2, and it's due next week. I gave the deadline by email. What did I say? It was, and that's what it is.
Thursday.
Okay. Remember that anything I sent has been archived in all over the place. Right? So even if you made me think otherwise.
Google it.
Okay, so what we're going to do today is continuing our discussion on PageRank. Basically, we just happen to be discussing PageRank, which is a second type of doing link-based importance. And then we'll look at a little bit more of that because we already did the authorities hubs computation. And then we will kind of discuss them side by side for much of today's class. So once you understand how first one works, how the second one works, then we will understand, we'll talk about how to combine these two with the similarity-based ranking that we have already done before. Okay, so you need to combine the similarity and importance somehow. So how do we do it? So that's the thing that we will discuss. And we'll also discuss, of course, which of these are more versus less stable, and which of these are more versus less robust. Okay. The difference between stability and robustness is that one is with stability with respect to random changes to the link structure of the web. The other is adversarial changes to the link structure of the web. Okay. So if I'm trying to increase my importance, can I do it? Versus somebody just happened to make a new page and put extra couple of links, would the entire world's importance measures be completely changed just because of this small random change? So that's the difference. And so we will see both stability and robustness issues. Okay. So that's what I am planning to do today. Are there any questions before I start? Okay. So we were looking at this graph at the very end of class last time, and we were trying to do how to do PageRank on this. So if you take the stochastic matrix with respect to this, it's essentially this. So for example, if you are in A, the only thing you can go to is C. So with probability 1, you go to C. If you are in B, with probability 1, you go to C2. If you are in C, with probability 1, you go to D. And if you are in D, with probability half and half, you go to A or B. And 0, 0, you go to C and D. That's the original unchanged stochastic matrix. Okay, and much of last class was how to make this matrix such that after you modify it, it will certainly have good properties. It will have stable stationary distribution. Okay, unique stationary distribution. Now notice that is one of these things that we do where the original stochastic matrix may already be aperiodic and irreducible. But I'm not going to check. I'm not going to waste my time checking. Okay, so if somebody asks you, go and wake up your friend, you don't need to check whether they are up or not. You just say, wake up. And then if they're already awake, it's okay. If not, they will be awake. Okay, so if it is not already irreducible and aperiodic, it will be after the changes we make. If it was already, it will still be after the changes we make. So we never actually, we'll always do these changes. Okay. So in this case, actually, is it aperiodic and irreducible, by the way? Is it aperiodic? That means, if it's periodic, that means it's a big cycle. You're just going from place to place to place. Is that the case for this graph? No. How about irreducibility? That means, is every node reachable from every other node? So in fact, I don't need to change anything here. And yet I'll change it anyway. Because I won't be wasting my time looking at a huge graph and checking whether or not it's aperiodic and irreducible. Okay? In general, at the web scale graphs, it's very, very, very unlikely that they would be periodic. It's extremely unlikely that the entire billions of pages of the web arrange themselves into a big cycle. Okay? Very, very unlikely. But there would be irreducibility on the web. In the sense, if nobody is pointing to you and you are not pointing to anybody, In particular, if you're not pointing to anybody, then you're a sink. So if anybody comes to you, then they'll not be able to get out. And if nobody is pointing to you, that means nobody is coming to you either. So you are still part of the web, and you're not reachable. So irreducibility is a much bigger problem. Basically, nodes are not always reachable from each other, and the changes we make will take care of both a periodicity and irreducibility. Okay? There was a question somewhere. Yes?
Yes. So when we say a graph is periodic, do we mean all the nodes perform a cycle?
It's just one single cycle.
Oh.
That's it. They make one single cycle. That's what it is. As I said, it's very unlikely for that to happen. Okay. Anyway, so basically after I make the changes here, so remember I talked about two changes. Change one is if there are any sync nodes. How can you tell if there is a sync node or not? If there is an all zero column, then that corresponds to a sync node. Okay? And if there are sync nodes, then in a sense, I go from, so then I essentially want to make sure that it's not a sync node. So I make a corresponding Z matrix, where Z matrix is exactly the same size as the M matrix, except it will have zero columns, all zero columns, if M matrix has a non-zero column. And when there is a zero column on the M matrix, then you will essentially put 1 over n, 1 over n, 1 over n, where n is the number of pages. So the assumption is that if you are a sync node, then you are not really a sync node, you will go to every other page with equal probability. That will break the cycle, that will break the unreachability issue. Now in this case, Z obviously will be 0, 0, 0 matrix, because there are no original zero columns, and so Z will not basically, Z will be an all zero matrix. Okay, so, and if you remember what we wanted to do is, we wanted to do M plus Z, and after you do M plus Z, this matrix will no longer have sync nodes. Okay, no longer have sync nodes, and then what you are going to do is we're going to also add a reset matrix. What do we call the reset matrix? K. Okay, reset matrix K, which is basically, in this case, we'll just assume that the reset matrix is 1 over n, 1 over n, 1 over n. So it's all elements of that matrix are 1 over n. Okay, but however, keep this in mind, we will actually play around with reset matrix. One way you can change PageRank behavior significantly is by reinterpreting the reset matrix. As I said, one way of rationalizing what you're doing here is essentially to say that with probability P, or in this case I think I call it C, with probability C, I would do whatever the page is asking me to do. And with probability 1 minus P, I will just reset myself. I'll stop following this particular search episode of following link after link after link. When I reset myself, the question is, where do I go? Okay, so this one is saying that I just randomly teleport myself to some other page, such that that random teleportation has the property that each page in the big bad universe has equal likelihood of being linked. That's what you meant when you said 1 over n, 1 over. Okay, now, in fact, this is not true for you, right? If you basically are bored with what you're doing, then you go off and reset yourself to some page, but that page might depend upon who you are. Different people have different different kind of home pages, the ones that they get to, that they go back to more often, if they're not doing anything else. You see what I'm saying? So in fact, you can make this importance measure more customized to individuals by changing their reset matrix. Okay? And you can do other things with this too. So keep this guy in mind. Right now, we're just going to make it to be uniform. That means every page is equally likely to be transitioned. Okay, so that's what I would do. And so in this case, 0.8 times m plus z plus, in this case, I just assume that all I want is the probability that you will do what the page is saying better be much bigger than the probability that you would not do what the page is saying. Because if in fact p equal to 0, then essentially you completely ignore the matrix, completely ignore the web graph, the graph that was given to you. Okay, and so it's more like 0.9 or 0.8 here, or 0.2 or 0.1 here. Now what exactly should be the number? I can't tell you. All I know is this, as long as this is not 0, if 1 minus p is not 0, then the Markov chain you get will have a stationary distribution, will have a unique stationary distribution. And notice that as you keep modifying the probabilities, you will get different stationary distributions. And this might, if you are into one of these people who believe that there is an objective importance metric for everything in the world, then you should be thinking, how can I do this? I mean, every little fudge factor I change, my importance of the pages is changing. But that's the way it is, really. Okay? As I said, what matters is stability and robustness more than, it should be a reasonable, it should be capturing your reasonable intuitions of PageRank, of importance, and then within that there is still a large number of different rankings of pages. Okay? So that's basically what we're doing here. So in this case I took 0.8 times n plus z plus 0.2 times k, where k is of course 1 over 4. So 0.25 all over the place matrix. Okay, so then if I compute that, then I'll get m star, which is this matrix. Now if I do PageRank on this, basically, which is again computing the primary eigenvector of the stochastic matrix, and the fastest way to compute it is power iteration. In fact, the fastest way PageRank is computed is power iteration. That's the only way you can do it. Okay, and so I start with any arbitrary initial probability vector. You could, for example, assume 1 over n, 1 over n, 1 over n, and then multiply m star by that probability vector. That probability vector by m star, you'll get the next probability vector. Multiply it again, you'll get the next one. Multiply it again, you'll get the next one. And in between two iterations, if the change is small enough, then you stop iterating. Basically, the probability hasn't changed from one iteration to other. That's the definition of steady state, right? At the steady state, the probability that you will find yourself in A versus D versus C versus B will not change even if you multiply that vector by m star. It will still be the same. In the beginning, it will change, but at the steady state, it won't change. And you ensured all this stuff that you did until you came here is to ensure that when you did the steady state, you will get to a unique probability distribution. You don't know what it is, but it will be unique. And first, you don't know what it is, but we know. The oracle knows what it is. That would be just the primary eigenvector of this matrix. Okay? Right? So, if I were to do this, essentially, actually, I mean, if you can do it yourself, iteration by iteration. But in this particular case, I just called MATLAB and found that essentially the eigenvector that the MATLAB gives is this, 0.338, 0.338, 0.636, and 0.605. Now obviously, this is not a probability distribution for a very small trivial reason, because the numbers don't add up to 1. I can make it add up to 1, I just divide this by the sum of all, divide this by sum of all, divide it by sum of all. And then I'll get 0.176, 0.176, 0.332, and 0.315. Okay, so what this is saying is C apparently is the place where you are most likely to be found, because you have a 0.332 probability that you'll find yourself at C. A random surfer would find herself at C. And then a 0.315 probability that they'll find themselves in D. And then A and B are pretty much identical, and you are likely to find yourself there with 0.176 probability. So now I'll just say that if I have to sort the importance, then the importance is C is the most important, then D, then A and B. And if I want to give an importance number, those numbers are these probabilities. Okay? This is basically what PageRank does. This is exactly what it does. Okay? Now, so I'm taking the same matrix and I'm actually now showing you the full eigen decomposition for this matrix. Okay? As I said, since this is not, since the stochastic matrix is not symmetric, it's not symmetric, right? And so the eigenvalues don't have to be all real. Okay? However, it just so happens that if it is a stochastic matrix, the primary eigenvalue will always be 1. I mentioned that to you. Okay? And so in fact, if you check, this is the eigenvalues 1, and a complex number, another complex number, that's it. Those are the eigenvalues. But you don't care about these eigenvalues, you only care about this one, and you take the eigenvector corresponding to this one. And within a minus plus minus sign, remember that if this and this are x and y axis, so are these x and y axis. Right? Okay? All you care about is the direction, all you care about is the orientation of the vector. Okay? And so, in this case, actually, I wound up getting all negatives, but just, you know, if the some are negative, some are positive, you are in big trouble. Okay? But you will only get all negatives or all positives. If it's all negatives, just ignore the negative sign. And then you got basically normalize it to probability. So assume this to be a distribution. Since it gives the unit vector, then you again divide it 0.3380 divided by the sum, 0.3380 divided by the sum, etc. And that's how I got my numbers. Okay? Okay. Now, I did PageRank on this, but before I used to do authorities hubs on this. Okay? So I want to do authorities hubs on this. Now, why not do the same thing? You know, take the same input and do two different things. Okay? So if I were to do authorities and hubs, basically the eigenvalues for the basic, remember the way authorities hubs was done. It will be taking A transpose and A transpose A and take their eigenvalues. And those will have the same eigenvalues, but they'll have different eigenvectors. Okay, so these are the eigenvalues 2, 2, and 1. Okay, and then the eigenvectors of one of them is the authorities, the other is the hub, the primary eigenvector. So in this case, this is the authority one, A, B, C, D. Okay, and the hub is this one, again, so A, B, C, D. So what this is saying is that if you were to look at this graph, the biggest authorities are A and B. Everybody else is equally bad authority. Okay? And the biggest hub is D, because D is pointing to A and B. Right? And they are locally consistent. If A and B are the biggest authorities, and if D is pointing to A and B, then D becomes the biggest hub.
And what?
What?
C is the biggest authority, right?
What? No, see, so the point of course is that this is one consistent interpretation. Again, we were talking last time about how your local intuitions may not actually wind up being the globally consistent eigenvector. So remember, I think last time we had a situation where one of them we thought should still have some hub value, but it just became 0 hub value. Okay, once again, if you were to do the eigenvector or the power iteration, this is what you will get. Now you might say, I don't like it, in which case invent your own new importance measure. Okay, but I mean I can make some sense of this, right? I mean in general, remember authorities and hubs would make lot more sense if you have pure authorities and pure hubs. Once you don't have it, then you know your intuitions are slightly off. Okay, so that's what you get here. Now, by the way, here's an interesting thing. The eigengap here is 0. You see that? You know, eigengap here is 0 because the primary eigenvector and the primary and secondary eigenvalues are both 2. These are really bad kind of matrices. Okay, so if you in fact were to do the power iteration on this, it will converge really slowly. Okay, in fact, you could actually argue, in fact, that both of these are primary eigenvectors. They're both 2. Right? So I told you one story where these are A and B are the authorities and D is the only hub. I can tell you a different story where C is the only authority. Okay? And A and B are the only hubs. Which one do you prefer? Take that. So it's like People magazine version for Tempe, People magazine version for Los Angeles. Both has, you know, a ranking of the sexiest people. And they just give, you know, a reasonable ranking that you might be happy with. Do you see what I'm saying? Actually, it's actually a very interesting point that I did not even realize it before coming to the class. This is like your worst dream come true, where eigengap is 0. That means you have 2 primary eigenvectors. It's like you have 2 right hands, or if you're left-handed, you have 2 left hands. Okay, and then which one is better? Well, both are same, exactly the same. Okay, so you can either think of this as the authority hubness, or think of this as the authority hubness. Both make sense.
There should be a way of prioritizing like which one to be taken what.
That's exactly my point, right? Suppose, no, all I'm saying is either you would get this or get this, and you would be happy with one of, you know, whichever you get. Do you see what I'm saying? I mean, the number of complaints you will have about which is the most livable city in the US, you know, we had enough of the sexiest things, so let's look at livable cities, okay? The only thing you'll get into trouble is if you suddenly find, you know, Detroit to be the most livable city at the top. Because most people seem to think that's not necessarily the case, except the people from Detroit. Okay? So as long as you put the really bad guys after ranking, you know, random number of people, and especially nameless places like Tempe is the most livable city. The people in the East Coast might think, hey, maybe that's true. Who knows? You know, at least it's not Detroit, in which case I would have proved that to be wrong. Do you understand what I'm saying? So that's more or less what's happening. These two, this are both consistent. And you can't do any better than this. And I mean, I could have made a better example. I didn't even realize that it is such a nice example until I came to the class today. But it's just a great example showing the futility of imposing orders, you know, beyond a certain level of precision. Okay? That's good. Okay, so now let's go to another example since we are into this. Forget about this sheet of copy earlier. So I'm now looking at a different graph, just one more example. So you can, for all these examples, you should be able to reproduce these results. Okay? One more example, this is this time this graph, okay, link graph. And then, of course, it has this particular adjacency matrix. Okay? If I do authorities hubs, this is a much nicer graph because it turns out, actually I don't, yeah, so it turns out that it's a much nicer matrix because this is 4.5, this is 1.0. There's a big gap. So there is no 2 different ways of looking at importance. Okay? And according to this, then, this is authorities and this is hubs. Okay? So essentially, according to this analysis, the biggest authorities are P1 and P2, which sort of, I guess you will agree. And the biggest hubs are Q1, Q2, Q3. Okay? And in particular, you are essentially saying that Q2 is not as good a hub as Q1 and Q3, which sort of makes sense because Q2 is only showing to P1, one of the authorities, whereas the other 2 guys are pointing to both the authorities. Okay? So here is a much well-behaved example where there is, you know, one ranking that mostly everybody will agree with. But the math, as far as the math is concerned, both are reasonable, essentially. And I believe that we live in a world where you can't really tell which is the most livable city. You know, between 2 very close cities, you can't really tell which is the most livable city. You know, a ranking with this as first and this as second first would be fine. Okay. Yes.
I know you have a matrix up there, but I don't understand why you're picking those 2 values in the 5th column.
Which one? No, because this is the primary eigenvalue.
Oh, because
and the vector corresponding to the primary eigenvalue. That's a very good question, but you should be, you know, able to capture that. The vector corresponding to the primary eigenvalue is the primary eigenvector. Remember that on a large-scale matrix, you won't actually do the eigen decomposition. It's waste of time. What you would instead have done is done the power iteration on just authorities and just hubs. Right? and that you would have just gotten this and this without ever having gotten the rest. But here I could just show you the entire situation. Okay? Yes?
Does usually points that have zero authority, or just this example?
No, again, remember that this is a consistent set of scores, and that would make sense. So, one most important thing is, if this were to be the stable authorities and stable hubs, then if you do one more iteration, they would remain the same. That's how you know it is stable.
My question was, can a hub be an authority also?
It's possible. Yes, in this example it did happen. Okay? In general, a node has both an authority and hub score. Okay? And again, the way this is, the reason both of these, reason this as well as this are considered answers is because you can start with this and you will remain with this. Or you can start with this and you will remain with this. Okay? You guys should be thinking in the back of your head, I mean, if you are putting things together, that it's almost, if you forget about the fact authorities hubs, we made a huge deal in PageRank about not getting unique distributions. Right? You did not want a Markov chain which has multiple stable distributions. Right? If you have two disconnected components, if you fall in this component, you'll only stay here. If you fall into this component, you'll only stay here. So, and both would be correct. If you fall into this component and you do one more iteration, you will still be here. If you fall into this component and you do one more iteration, you will still be here. So either of them would have been reasonable. It would have been stable. But they were not unique stationary distributions. So we went over backwards to give a stable distribution here. We didn't particularly care about it in the authorities hubs. As we go on a little further today, I'll tell you, we could have done what we did to PageRank, also to authorities hubs. In which case, this business of eigengap being 0 wouldn't have been there. See what I'm saying? Okay? But I'll tell you that, I sort of told you that I'll be telling you. Okay, so that's for authorities hubs. On the same matrix, if you were to essentially do the same idea of 0.8 and 0.2, 0.8 as a p, and then 0.2 as 1 minus p, obviously, and then you assume that the reset matrix is 1 over 5 all over the place. And once again, Z would be all 0 matrix because there are no sync nodes. Oh no, well, there is a sync node. P2 is a sync node. So this is a case where Z would have, for the P2 column, it will already have 1 over 5, 1 over 5, 1 over 5. Okay, so 0.8 times original M plus Z plus 0.2 times the K, which is all 1 over 5 all over the place. If you do that, and this is something that you can do when you go home, you should get this matrix. That's M stuff. Now, if I were to do the Markov chain analysis on this, if I get the primary eigenvector for this, then essentially, once again, notice that this is 1.0, and this is already negative, this is complex, this is complex. But thankfully, all I care about is the one that corresponds to the 1.0 eigenvalue. Okay? And then, with respect to that, you essentially see that, that this is 0.6, 0.1, 0.1, 0.5, 0.4. Of course, once again, you should make it into a distribution by dividing each number by the sum of all the numbers. And you'll get a probability distribution. But the order will be the same, right? So, essentially what this is saying is P1 and P2, in fact, Q1 is the most important place according to PageRank. Because you are likely to get to Q2, you're likely to spend most of your time at Q1. Because it has the highest probability. Okay, the next highest is Q2, then, the next highest is P1, then P2, then Q2 and Q3. Once again, your intuition sort of hold. Notice that had I played around with the P, instead of 0.8, I wrote 0.9, these numbers would be slightly different. In fact, this is the kind of thing you can do at home. You can take the same exact matrix and play with different values of P. And numbers would be different. The question is whether the ranking would be approximately similar. It's not necessary that the ranking will remain the same either, because you'll have a new Markov chain which has its own stationary distribution. Okay? So eventually, everything that's guiding us is not figuring out what is really the importance measure, because there's no way of defining it, but is providing a measure, an algorithm which has a well-defined fixed point. Okay? That's basically what it is. So, any questions on this?
Difference between PageRank and
So, okay, so the question is, can you make any sense of it? There is no obvious way of making any sense. So the difference between US News and World Report's ranking of the universities versus Times Higher Education Supplements ranking of the...
So we are,
you can't be sure.
according to one, where ASU is in the world is within the 100.
Yeah.
And here in the US, we are not even.
They are not, yeah. So basically, that's all we can say is they are locally consistent, but you can't really compare two completely different kinds of rankings. So all you could see by just looking at this picture, it's not a proof, is that big page rank, so big authorities do seem to have big page rank. Okay, but pure hubs have low page rank. Q1 is like a part hub, part authority, it still has good page rank. Okay, basically, people are, it's like the view of random circle model here is that a lot of traffic is being pushed to P1, and then P1 is pushing the traffic back to Q1. So Q1 is not a good one. You will wind up spending a lot of time. Okay, so that's basically the comparison I can make, but this is something you could just look at the slide and realize yourself. There is no obvious, if your authority value is this much, your page rank value will be this much. Okay, notice also, as of now, that I did not doctor the adjacency matrix, but I doctored the heck out of the stochastic matrix, which is really adjacency matrix transpose, normalized. Okay, so basically what you're saying is, how come this guy gets all this extra treatment and this guy doesn't? Right, and you and your friend probably put up these houses in who has the most beautiful house, and your friend's house, is getting extra treatment before it actually takes part in the competition, and you are not getting any. Okay, you should ask, why am I not getting this? Why am I not getting the treatment? Okay, so you can in fact ask that question, why can't you do this for the adjacency matrix? Actually, you can. Okay, I mean, you start thinking about, this is what we'll say in a minute later again, but instead of thinking in terms of 1-0 matrix, the adjacency matrix might be, the numbers there might be the strength of the connection. Instead of saying there's an edge, you say, what is the strength of the edge? So not all edges have to be created equal. Okay, so in particular, that allows you to put weak edges between everybody and everybody. Just like when I, in essence, put, weak transition from any node to any node, I have, in the adjacency graph, put a weak edge between any node and any other node. So really what you should do is do authorities hubs on the adjacency matrix that corresponds to M star, which is not all that hard to compute. Right? M star is now some adjacency matrices transpose normalized. So you can compute that adjacency matrix. And then you can do this. Then you are really comparing apples to apples. Or at least apples to something which sort of looks more like apples. Okay? But in fact, the interesting thing is even putting these two in the same slide and talking about the connections is something that wasn't done for the longest time. Because if you come up with your idea and your friend comes up with their idea, you don't want to acknowledge your friend's idea. And so you just talk about your idea, your friend talks about their idea, and then just leave it. Okay. but this is this is a class, so I get to actually compare them. Any questions on this slide? This should make you should understand this stuff basically. Spend a lot of time on this, and once you understand this, you pretty much understood. I mean, the computation itself is mindless. The interesting question is, what are the properties of the computation? And are you giving unfair advantages to one computation as against another? That's what I was thinking there. Yes, there's a question.
So what is the second column in this after Q1?
This one?
Yeah.
This corresponds to this is the secondary eigenvector. So, in fact, one of the interesting questions, this is the secondary eigenvector. There is no obvious physical interpretation for secondary eigenvectors of Markov chains that I am aware of. Okay, but in fact, the cute thing is that if you read the JACM paper of, on authorities and hubs, which, by the way, is probably the only JACM paper you'll ever read. JACM is considered like the flagship journal of computer science. Okay, and it completely follows the Mark Twain's definition of classic, where Mark Twain says a classic is something that everybody wishes that they have already read and nobody actually had. Okay, JACM is considered the most important journal, and obviously a few people read it, but the masses don't read it. Okay. Mostly because it tends to be highly theoretical. But this is a paper that you actually can read. And then you can write in your resume, also read a JACM paper. Believe me, that's kind of good. Okay, and so if you do read the JACM paper of John Kleinberg, then you notice that at the end of his paper, he starts thinking, well, I use the primary eigenvector as authorities or hubs. Okay, in one primary eigenvector as authorities, one primary eigenvector as hubs. Okay, what will I do with the secondary eigenvector? Is there something that I can say about them? And in fact, he comes up with interesting speculations. In particular, he actually makes this claim that secondary eigenvector is connected to the clusters in the link matrix. Remember, one of the interesting things is he allows link matrix, he doesn't doctor link matrix. The original paper of Kleinberg did not doctor the link matrix at all. Okay, and what happens then is that essentially you could have multiple disconnected components, and finding each separate disconnected component is finding a cluster. And he was able to actually sort of make connections between the secondary eigenvector and the clusters. Today we will talk about that a little, but in general people have thought of if one eigenvector has some use, then maybe we should look at other eigenvectors and see if they also have any use. Yeah.
So just by looking at the values, doesn't this thing gives us a better understanding of hubs and authorities? This matrix, because all the hubs are negative and authorities are positive, and the
that's not. You're just looking at that's okay. Just you're looking at it like this. I mean, it's not guaranteed.
Yeah.
I don't have a proof. Okay, so that could be a Rorschach blot test. I mean, you're just looking for something to give you direction, and you say, yeah, I got a sign now. That's what your sign was, but that may not actually be valid. Any other questions? Yes.
Does the negative value mean anything here, or you just neglect the negative value?
In this case?
No, on the primary.
No, all negatives is fine. Basically, as I said, if this is x-axis, so is this x-axis. Okay? Okay, so what I will do now is, all this while you are looking at importance computation. You computed the importance of the pages. But before you did this, you computed the similarity of the page to the query. How are you going to combine these? You have not thought about it all this while. I mean, there was a ranking of pages in terms of how important they are, and there's a ranking of pages in terms of how similar they are to the query. I want just one ranking. The user wants one ranking. How am I going to compare importance and similarity into a single rank? Okay? And so we will talk about two different approaches. Both make sense, but they have trade-offs. Okay? One idea is a global importance measure. Okay, so every page has a global importance measure, and then essentially every page has a query specific similarity measure. Okay, so you then combine the importance with similarity by combining apples and oranges. How do you combine apples and oranges? Alpha times apples plus 1 minus alpha times oranges. Okay? Basically just, there is no principle here, essentially. It's like, there is, your score in midterm is this, your height is this, so your final grade is 0.5 times your midterm score plus 0.5 times your height. And if I did that, and if you leave me alone, then that's what I'm doing here. Importance and similarity have no real connection, and yet I'm combining it. Okay, so the disadvantage is important is, so one issue is, of course, you're combining apples and oranges. The second issue is, it assumes that importance is query independent, because you computed the important even before you saw the query. Right? Okay? So, that's not the way we think of importance. Like if you have a computer science query, then presumably you will talk to me as again as some other computer science professor. Hopefully. Okay? If on the other hand you have a sociology query, you should not be still assuming that Rao would know. Do you understand what I'm saying? There is an importance of sociologists, there's an importance of computer scientists, there's an importance of sports broadcasters, there's an importance of baseball teams. Okay? And there is no global importance measure at all, really speaking. So if you were to do this, then you are essentially saying there's just a global importance measure. And obviously, you could get into trouble where you will wind up taking a page which is sort of important in a big area and assume they are also an authority on this small area which the query is about. Do you understand what I'm saying? So for example, you might essentially assume that the best writer of novels in English language also would be the authority on a computer science query. Because probably, they have much, there's a large number of people who are giving them importance, but they have no clue about computer science, probably. Okay, so that's what global importance measure has a disadvantage of. But what's the advantage? The advantage is you get to do it once and forget it. So you just compute the importance measure for all the pages up front and then just forget it. And when the queries come, all you're doing is you compute the similarity quickly using your inverted index method. Okay, and just before you rank, you do like alpha times importance plus 1 minus alpha times similarity. Okay, the only thing that you would do is, to say that if similarity is greater than 0, if similarity is equal to 0, then rank is 0. If not, rank is alpha times similarity plus 1 minus alpha times page rank. An importance measure. And when I say page rank, you could use authority up there too. I'm not really talking about this. It actually turns out that page rank, the original paper, used this view of importance computation. But there was no reason that page rank should be done only this way. Okay, it's just the question is, when do you want to compute importance? Very specific way or very independent?
It's very likely that this one will have a lot of correlation with the query specific one, because if they are similar, if you are only considering similar documents here for, so
yeah, but I mean, I can make up. So the question is, I can easily get you counterexamples where the ranking would be wrong. So for example, I'm only saying similarity equal to 0. So what if I have a page 1 whose similarity is 1.0 times 10 power minus 80 greater than 0. Okay, and importance is 0.9. And another page whose similarity is 0.5. And importance is 1.0 and times 10 power minus 7. So you're now likely to give pages which have importance as answers, even if in fact their similarity to your query is not as good. Now, all I did was to give you a counterexample where this can happen. For me to convince you that this actually happens in the queries you're doing on the web as it exists, I need a much bigger experiment. And I don't know what exactly will happen in that kind of an experiment. Okay? But you do know what are the trade-offs that you're getting yourself into. Okay? The other option is completely query specific, which is you compute the importance only on the subset of pages that have a similarity to the query above a certain threshold. Do you see what I'm saying? So this way it's somehow much more systematic. You first use one to get the set of pages that you want to rank, and then the other to top second rank. Okay. In particular, what I can actually do is, for example, and I'll say this in a separate slide, but basically what I'll do is I'll let's say take top 100 pages that are similar to the query. Okay. Now, of course, I can just try to do importance measure directly on them, but they don't necessarily point to each other. So what I do is I take backlinks a few levels behind this and a few levels forward links. So the idea is I got, let's say, these are my the pages that are in the top 8 answers. Then I will consider all the pages that are pointing to these, and also all the pages that these guys are pointing to. And when I consider them, they may still have additional links. I got this page into the set because this is being pointed to by one of these guys. But then this guy also might actually be pointing to this guy. You see what I'm saying? So then this thing is called a base set. It's like you're taking the graph that is sort of rooted near these vertices, going a few levels back and few levels forward. You're taking that subgraph and you're doing importance analysis on that subgraph. If you do that, then in essence you are doing query specific, highly query specific importance measure. Okay. Now it turns out that the advantage for this is importance computation is very sensitive to the queries, but the huge disadvantage is that this computation is being done in the costliest temporal real estate during search, which is after the user hits the return button and before you start showing them the results. You see what I'm saying? So saying, you give me a couple of days, I'm just going to quickly do this, is not going to work. Even saying, give me a couple of hours is not going to work. Even saying a couple of minutes is not going to work. Okay, so if you're talking about fast response search engines, it's sort of a kind of a dead on arrival idea, because if you have to do any additional processing, which this will have, because now you have to compute this and then do power iteration on this. Okay, which is basically what John Kleinberg originally proposed with respect to his authorities hubs computation. Okay, but it could be done for PageRank too. And similarly, what PageRank is doing could be done for authorities hubs too. Whether you do global or local analysis has nothing to do with authorities hubs versus PageRank. These are orthogonal choices. And they have their orthogonal trade-offs. Okay? Now the interesting thing, of course, is can you do something in between? This is all global, and the advantage is you get to do work beforehand. And this is all local, but the disadvantage is that you do wind up working only after the query comes. So the question is, can I get some middle ground? Yes?
By doing very specific, aren't you defining the whole purpose of the importance? If you're just looking at the documents that are similar, might as well just look at the documents that are only similar, but not even do the importance.
No, because remember, one of the interesting things that can happen is that this guy came into the similarity, right? Let's say, but in fact, notice that when I get this graph, right? When I get this graph, remember, once this guy is in, anything that this guy is pointing to is also in. Right? I mean, the way you take, if I give you a graph and I say, So if I give you a graph like this, let's say, okay, and then I say keep just this and this, right? Then essentially the only link that's gone is just that. Okay, in doing so, you might wind up bringing in nodes that are actually more important than the ones that wound up having high syntactic similarity. I'll show you examples, and if you really don't, if you want to see more compelling examples, read Kleinberg's JSAM paper. He actually gives examples where this happens. Okay, it's a good question, but you need to convince yourself that this does not. But I still have my question up front, which is how are you going to do something in between? Can you do something in between? All I said was the problem with this is that they're saying there's one single importance measure for the entire world. And this one is saying there's one importance measure for each query. Okay, because these two already started. Okay.
It was the very specific for every term or ratio.
Not term, yeah.
So you can cluster your data set that you have before, and you can do mini page ranks on different clusters depending on topics, and then
Clusters, no, it's not really as much of a cluster. I mean, remember the example I gave you. I said there's a sociologist, there's a computer scientist, and there is something else, and there is an importance ranking for sociologists, there's importance ranking for computer scientists, right? And it's not too hard to actually come up with importance ranking for each of these topics, each of these groups. Somebody, I think whoever said clusters, you could assume that that's sort of close to what you're saying. Okay? So the idea is you can do a topic-specific importance measure, but statically. That is, before even the queries come, you make the assumption that the queries fall into these 100 topics. They might be queries about computer science. They may be queries about Hollywood. They may be queries about sports. They may be queries about sociology. Okay? These are my topics. So then, for each of these topics, I compute an importance measure. Okay? Now, when the query comes, I use the right set of importance measures. Of course, how do I do that? I need to classify the query into its topic membership. It may be like a binary Boolean classification, that means it actually belongs to this topic, or it could be a fractional classification, saying this query is 50% about sports, 20% about computer science, and another 25% about sociology, let's say. If I were to give you the class of the query in terms of these topics, then the topics are the intermediaries. Each query gets mapped into the topics in terms of its fractional membership, and each page has an importance with respect to each of these topics. So then you can compute the effective importance measure as the weighted summation of the importance measures, where the weights are your fractional membership of your query onto the topics. Okay, this is a pretty neat idea, and essentially this is like a topic-specific PageRank computation. In fact, the paper that did this first essentially did it only in the context of PageRank. But as I say, you could do this either for PageRank or other papers. It's an afternoon issue. Okay, so you're essentially deciding topics before even the queries come. And pages have membership into topics. This page may have importance of 100 out of 100 for computer science, and only importance 1 out of 100 for sociology. And this query has 0.5 sociology query, 0.5 computer science query, because it's probably looking for what is the most interesting sociological work that's being done in computer science. And if you think there is no such thing, you haven't read New York Times Today, for example, because there was like blindingly obvious study about the fact that people tend to be crotchety in the middle of the night and are much happier when they're awake. And so they did this by looking at the Twitter messages of gazillion billions of people, and they essentially did the sentiment analysis on these Twitter messages, and they found that people who are posting this at like 1 o'clock in the night, local time, they seem to be meaner than the people who are posting it at like 12 o'clock in the afternoon. Sociological work using computer science. And it gets you front page New York Times, which is, as far as one can say, is as much publicity as you can get, right? Okay, so that particular query then needs sociology and computer science importance measures to be combined. Okay, the reason this is still a good idea is compared to this, it has more page ranks per paper, per page. More importance measures per page. Each, for each, in essence, what you're doing here is each page has a separate importance measure for each possible query of the word. Here, each page has just one importance measure for all the queries of the word. Here, each page has one importance measure based on which set of queries you are considering. A set of queries is a topic. Okay. Now, the only thing this guy does at the runtime is that is in the after the actual query has been given. The only thing they do is essentially classify the query into the topics, which is cheap. The difficult stuff of doing, power iteration on large-scale matrices is still done beforehand. You see? Okay? So that's basically topic-specific view of importance measures. Okay? So now, how to combine importance and similarity metrics? I sort of told you while discussing that. Okay? So if you do query-specific importance computation, then you first do the similarity, then you do this base set, and then you compute the importance on that base set. Very systematic. If on the other hand you do global importance computation, then you need to compare apples and oranges. So that's the other one where I said if your similarity is equal to 0, I don't care how important you are. If you have 0 similarity to my query, I don't want you. Okay? And if your similarity is not 0, then your overall rank is alpha times similarity plus 1 minus alpha times importance. Now, where is the alpha coming from? It's a fudge factor. You figure this out. Okay, whatever is working well. Okay. So that's basically the two approaches. And in the topic specific, I told you the third way of doing it, which is basically as the query comes, you first convert it into the topics, and then you do the weighted summation of the importance measures of the topics. Okay. Okay. So this basically is showing. This is showing what I showed there, which is authorities hubs essentially gets the similar pages and looks at some pages k levels this side and k levels this side. K equal to 1 normally, but you can do k equal to 2, and if you do k equal to infinity, you get the entire graph. Right? Okay? And so there's a way of making it more and more global by just going more and more levels back in terms of backlinks. Okay? And so then you do this, and then with respect to this subgraph, you then compute your importance measure. Authorities hubs happen to do it that way, but you could do PageRank this way too. Nothing stops you. Okay, and the other one basically is what PageRank did, where if similarity is greater than 0, then you do W times similarity plus 1 minus W times rank, the importance rank. Otherwise, you give 0. Now, of course, you can do small tweaks, small changes. For example, you can say if similarity is about a certain threshold, you do this. Otherwise, you just throw the page. You can do that if you want. But 0 is like special because 0 means essentially there's no connection to that page and you're okay. Okay. Now, PageRank originally did it this way, and the last time Google actually published a paper about how they do ranking, they said this is how they do it. But that, don't keep your hopes too high. It was done when the two kids were students at Stanford graduate program. Okay. Exactly what currently a particular search engine does, I don't know. Okay. But those are the trade-offs that you want to understand. So, and this is something that you got out of this discussion, which you may not get by reading each paper separately, which is I put them next to each other, and I point out to you that there are two alternate ways of computing page importance, and there are two alternate ways of combining importance and similarity. Okay, and in some sense, this is PageRank versus authorities hubs. You can pick either. Both of them are reasonable. And you can do either of them before query time or at query time. Okay? So any pair of alternatives would work as a workable ranking measure. And project 2 really is just going to be doing this for both authorities, hubs, and PageRank as a standard form. But if you're interested, you can combine and then do. That means you can, for example, do PageRank with respect to the query time computation and authorities hubs with respect to stationary computation, global computation. There's nothing in the definition of a Markov chain or the adjacency matrix that makes one to be global, one to be local. Okay? We see, we have 15 minutes. Actually, this is the actual slide on the topic-specific PageRank that I described to you. I might come back to it next class, but essentially it has the details. Okay. One interesting question. Actually, let me do this. So what I'm going to do now for the next 5 minutes is a second-order issue. Whether you can make links be. So this is all link-based analysis, right? Now the question is, of course, I'm sort of starting to think about stability and robustness. Okay, so the question, of course, is can I make sure that only the relevant links are taken into account to begin with? Relevant links are taken into account to begin with. So from my page, there are lots and lots of links. Okay, but maybe if your query is about computer science, the links from my page whose context is computer science are more relevant than the links from my page whose context is some other thing about my life, like faculty politics. Right? So now normal link analysis assumes all links are created equal. So if you're talking about query specificity and topic specificity, can we not consider the links also in terms of the topics? Okay, so this is something that almost left it in the back without going into it earlier. But now I will say, well, you can. The question, of course, is there's a simple idea, which is if you want to remove some of the spam links, one simple idea that used to work a long back when people started thinking about link analysis is consider links from one domain to a completely different domain to be more important than links from one domain to the same domain. So you talk about intrinsic versus extrinsic links, and somehow links that I make to pages within my own domain, where my own domain is, let's say, ASU.edu, are given lesser weight than the ones I give to outside of the domain. This made a whole lot of sense when people couldn't buy up domain names for pennies a day. Right? Now, of course, you can buy any domain name, and then basically I can have a mirror of ASU.edu called a different domain name, and I'll put that link to that. And so you can't actually tell whether it is a transverse link or a intrinsic link. Okay, but this might work sometimes. But a much more interesting issue is the link connected to the topic or the query you are looking at? Now, this analysis makes most sense actually if either you are doing topic specific or query specific importance computation. If you're doing global importance computation, then really all links are created equal. There's nothing you can say. Okay. If you are doing topic based importance computation or query based importance computation, then I can check whether a link is related to my topic or my query. How do I do that?
I'm going to the document that is going.
So the idea that we will do is essentially, what is a topic? And what is a query? What's a query for us?
Set of topics.
Its query is just a bag of words. What's a topic? They're also a bag of words. But it doesn't matter. I mean, they're also a bag of words. I mean, there's no separation in words, right? I mean, it's like, so topic is also a bag of words. Query is a bag of words, right? Now, if I have a page, I have a page, and then some text, and a link, and some more text. Now, if in fact, you are following the HTML standard, you normally are supposed to put anchor text in the href, right? If you do that, then you are describing the link. Okay, many a time, unfortunately, people will say click here, only here would be included. And here is not a particularly descriptive term. But then what I can do is I will take a window for, keywords here and a keywords here, before and after the link. That will give me a bag of words. I have bag of words which is the context of my link. I'm in business now. I have a bag of words that's a query. I have a bag of words which is a topic. I have a bag of words which is the context of my query. And I can check whether or not it's relevant. The context is relevant to the query. How do I do that? Similarity, vector similarity. In fact, the second best way of doing pretty much everything in this class is to do vector similarity. Okay? But if you are in doubt, just do vector similarity. Okay. So yes, that's what you do. You compute vector similarity between the context of the query and the description of the context of the link and the description of the query and the description of the topic. Now you can, act all high and mighty and say, how can you say, context is really a bag of words, but then it's too late for that because you already said topic is a bag of words, query is a bag of words, page is a bag of words. You're already sunk. So saying context is also a bag of words is not going to make you sink any further. So you may as well make some sort of, it's like make some use of it. Okay, so the idea is that I can, when I have this sort of a, I got the K pages that are similar to the query. Then I computed the base set. Now, having computed the base set, when I'm doing the adjacency matrix or the stochastic matrix, I can put the weight on the link be proportional to the context of that link, the similarity between the context of the link and the query or the topic. If I'm doing at the query time, you do it to query. If I'm doing this whole thing at the topic specific page rank time, then I do it. It's a very powerful idea. Once again, if you're doing it at the query time, it will take more time, but if you're doing it at the topic time, it's still offline in you. Right? Okay. So now the interesting thing about this is it starts making you think about the context surrounding the link. Okay, and also made you think that the topics and queries are also bags of words. So that allows us to actually give the description of topic-specific page rank, which I mentioned earlier, but there were some details that were missing. In particular, first of all, how do you decide what are the topics? I said, let's assume computer science is a topic, sociology is a topic, something else is a topic. Okay. Now, here's an interesting way of thinking about it. If there are queries Q1 to Qn, okay, then the topics are nothing but subsets of the queries. So if there are n queries, how many topics are there? 2 power n topics. Clearly, that's not the direction you wanted to go. Right? You didn't want to increase the number of topics to be more than the number of queries. When we are talking about computer science is a topic, sociology is a topic, we kind of agree. We know how the world works, and we kind of agree these are important topics. How do you do this if you don't know anything about the world that you live in? Well, the idea that these guys had was there used to be open. Right now, I think there is an open. There used to be a thing called DMOS, which is an open directory project, and I think it now still exists. I think as far as I know. So, open directory project basically tries to put a top level. Humans try and put a top level classification of all the pages on the web. Okay, so you could use that. They, for example, say the pages in the web can be split into arts pages, games pages, kids and teens pages, reference pages, shopping pages, blah, blah, blah. So then a good thing is, now if I have no better ideas, then I can say that my topics are these top guys. There's an art topic, there's a kids topic, there's a games topic, etc. Okay? Then, if I have a topic, then how do I describe the topic? I need some kind of a bag of words for describing the topic. Well, I can take the bag of words in, take some of the pages from the arts and take the bag of words from that.